welcome this morning to 2018 Flash Memory Summit, specifically NVMe Express. What I wanted to do first is, see if I can see that far, is just introduce our speakers real quick. The NVMe Express team has 2 full days of really awesome content that we put together. It's going to kind of dodge and weave on all different types of, all over the spectrum, and we'll get into the agenda here real quick. But before we do that, I just want to introduce the speakers that we have for this track. So bear with me here. Jay Metz, where's Jay? Wave, Jay. There you go. We're going to make this exciting and engaging. Okay, so Jay is currently the R&D engineer for the Office of the CTO for the Compute and Server Group for Cisco Systems. Has a broad and eclectic background of both academic and corporate and industry experience, and I've had many engaging conversations with Jay on things all over the map, so if you ever want to know what he's thinking, just ask him. Maybe not. He's an award-winning public speaker, author, and contributor to industry trade publications. He has been active in industry standards with membership on the board of directors for Fiber Channel Industry Association, SNIA, and also is a very active member in NVMe Express on the promoters board. He's received his PhD from the University of Georgia. And then the next contestant on The Price is Right here is going to be David Allen. He is an NVMe board member and a senior director of marketing for NVMe products at Seagate. In his role, David owns planning, business development, and product marketing for platform-level solutions with Seagate Flash technologies, including software and SSD-level products. David, product?
That sounds excellent.
Yeah, it does, huh? David is also responsible for driving design wins with Tier 1 and Tier 2 level customers. Additional responsibilities include planning and execution of product launches, marketing activities, communication, and campaigns for his division. Previously, David was with PMC Sierra for over 4 years as a director of PCIe NVM product marketing responsibilities for the controller direction and the future of PCIe NVMe business. David also held similar roles in management, marketing, and engineering for 20 years in the storage and semiconductor industries. David has a bachelor's and master's in electrical and electronic engineering degrees from Oklahoma State University. Okay, and then myself, since I have to introduce myself, so you know, some of you I already know in the room, but I'm the Senior Sales Enablement Manager for SSDs and NAND products with Micron Technology Storage Business Unit. I joined Micron in 1989 and have spent the majority of my career in various marketing roles supporting NOR Flash, NAND, and SSD products with heavy focus on PCIe SSDs. I hold a BS in Business and Marketing from University of Phoenix, and I currently serve on the board of directors for NVMe and also co-chair the NVMe Marketing Work Group with John Michael Hans, who will be in the next session that I'm chairing. So with that, we will go ahead and go over the agenda, which I cannot see from here, so I'll let you guys take a look-see there. These are the things that we're going to try to talk about this morning. And with that, I don't expect you to memorize this next slide, but I really wanted to just kind of give you a quick overview of all the things that we have to talk about today. And you can see we're going all over the map from different architectures and applications. The next session that I'm chairing, we're going to really start to focus on how NVMe actually drives some key benefits in various different environments. So we'll talk about client, enterprise data center, and I think the storage as well. So, or excuse me, hyperscale environment. So if you can, I know 2 days is a long day. We don't expect you to be here the whole time, but if there's some interest there to you, please come back. Like I said, we're going to be here for the next 2 days. We are excited to get new followers with NVMe Express. You can follow us on LinkedIn, and you can also follow us on our NVMe Express website. It's a great way to get information on driver pieces. We usually put different news articles that are out there, blogs. There's all kinds of content out there. So if you don't already follow NVMe Express, feel free to do so. You can also join our mailing list. And we usually typically send out a newsletter about every 6 to 8 weeks, 6 weeks or so. Yeah. And then also you can follow us on Twitter as well. Okay, so does anybody not know what NVM Express is? Great. We're gonna push past the slide because I want to make sure that we have enough time for questions. All right. Okay, so just real quick, we're just gonna talk about the marketing landscape, and make sure we're on task here. I'm not gonna bore you with a ton of the market outlook. I think everyone's pretty well aware. PCIe continues to grow at a pretty strong rate. SATA is still kind of hanging in there, and SAS is kind of declining there. But overall, NVMe is pretty much the de facto standard for anything client-based or enterprise-based. So we continue to see a huge growth in PCIe in general, and NVMe is the perfect protocol to attach to that. It's opening a lot of different capabilities, lowering latency and improving performance. And over the next 2 days, you're going to see how all that actually transcends across the entire pipeline of the data center and even the client stuff. John Michael's got a really good presentation in this next track that goes over some of the key benefits within NVMe, and specifically in the client space, which typically on this show we don't really touch too much on the client stuff, but I think it's really important because the NVMe does bring some key benefits in that space. And with that, I'm actually going to switch gears a little bit. We're going to talk about the roadmap, so I'm going to turn it over to David Allen. David?
There's the clicker, and let me advance. Is it working? Oh yeah, there we go. Thank you. What I wanted to do today is just cover the roadmap at a top level. It shows the key components that the working groups are focused on within NVMe. If you look at this slide, that top row is the base specification. We've had generational releases of that base specification with key features that we've deployed over time. We look at 2014 as kind of one of the big kickoffs. That was 1.2. With 2017 1.3, we added features like sanitize for write amplification improvements, streams for write amplification improvements, sanitize for some additional security features where you basically go in and ensure that data that was on the SSD is been removed, and then some SRIV or virtualization capabilities. The other middle line there is NVMe over Fabric. That also encompasses key parts of the base spec, so that's why you'll see that dashed or dotted line around NVMe 1.2.1, but that's when the first specification of NVMe OF came out that allows really to provide scale for NVMe devices, and to do that over several different fabric types. And then NVMe MI, so NVMe over Fabric, Amber Huffman runs that working group, that technical working group from Intel. Peter Onufric, this gentleman back here, runs the NVMe MI working group, and that's where all the management features are rolled out as well within that. So they meet on a weekly basis, the technical working groups do. They work on each one of these key items that are listed in this roadmap, and they focus on those items, finish the specifications, and then those specifications go for ratification once complete. On the we're going to have details on each one of these pieces here, those slides. Really for NVMe, some of the key things for the base spec that we've been focusing on is improvements in QoS. As everyone knows, NVMe was created as a high-performance, very low-latency access to flash, or non-volatile memory types, excuse me. And as we continue, we want to ensure that we strive to make improvements there. And we'll cover some of these a little bit, but things like IOD, other devices, other implementations like a persistent memory region just allows for some persistency on some key data within a SSD itself or controller. And then also there's been some work done on multipathing, which will be suitable for fabrics as well as sharing of NVMe devices across multiple paths in the device. On the management side, really the key there is to have compliance across a broad range of industry standard tools, right? We have to ensure that the management tools can speak to all the devices that are connected out there behind the host as well as in fabrics. And those are really key to get all that data back up to the host. event logging. If anything goes wrong, you want to have a nice crisp event log for debugging, as well as sending management commands, understanding the environment the devices are sitting in, temperatures, thermal conditions, those types of pieces of information are carried back up. And those are all handled in the MI spec. On the networking side, it became evident we really wanted to be able to scale beyond just PCIe connections with NVMe. So Amber works on the fabric piece of this, and you'll see that we have multiple mechanisms for encapsulating NVMe commands and sending them down across the wire. There's fiber channel, there's InfiniBand, other pieces like that we have some details. And Jay Metz will go in detail after I'm done about some of the fabric implementations that are being worked on. Okay, let's talk about one of the key features on the base spec, and that's what's fairly new is I/O determinism. It uses all the standard NVMe constructs for an SSD device, and basically you can have multiple workloads or I/Os going to an SSD, and that SSD is treated as a single physical entity. So when there's background operations going on that SSD, that can cause backups or QoS latency issues with other workloads that are occurring on that SSD. So with I/O determinism, the idea is to break a drive into really 4 different physical devices that will allow for those workloads to independently access those physical chunks of the drive. It also helps to just manage the drive as well, because you'll have as drives get larger and larger, we're talking like 16 terabytes, 32 terabytes. You know, systems are used to using smaller chunks, so you get that benefit as well, just managing the drive in smaller chunks. And then when there's background operations going on one piece of that physical drive, it's not conflicting with the I/O operations on the other piece of that drive. So it really alleviates some of the latencies that are going on. As an extension into this, there'll be information that goes back up to the host that says, hey, this chunk here is not being utilized or not being used right now. There's no background operations going on this physical portion of the drive, so please use that for your activities. So these advances will really help with QoS in the systems. It's kind of a nice feature addition. Persistent memory region. So early on, the concept of controller memory buffer was added to devices. And this is basically a region of memory down on a device that is opened up to the host, usually as a PCIe bar type access for DMA access. Very high transactional, very low latency access into either the local memory of a controller or to DRAM that's usually attached to these controllers before it goes to flash. So that gives the host a nice little chunk of memory to just put some additional log data or whatever they need to have in that piece. However, previously if you had a rude power loss event, that data was not captured. So persistent memory region just takes a chunk of this memory or the entire piece of that and makes it persistent. So upon a rude power loss, this small, usually a smaller piece of memory is vaulted to flash so that it's there when the device comes back up, which is kind of key in enterprise systems. Multipathing namespace sharing. This allows for a host with multiple ports to access a namespace that's contained within usually an SSD. Information about those paths can be pushed back up to that host, and then the host can make good decisions about where that data needs to go and how it gets down to the device itself. So it allows for some congestion management. Jay's going to talk about this more in the fabric realm, and that's kind of the picture on the right-hand side where you've got multiple hosts connected to multiple devices with multiple paths. So it's a nice mechanism for allowing these devices to have high availability paths. If you have a path go down, you still have another path available, and then there's information about the traffic on those paths that gets passed back up to the host in case there's any really slow traffic that you need to route around. Okay, NVMe 1.4, the base specification. Oops, thank you. Oops, went too far. The base specification, 8 TPs have been ratified by that group. If you go to the website, you can go into each one of the detailed sections and specification on those items, and you can get additional details there. You're also, welcome, involvement in the technical specification process. So those that want to get involved, more than happy to have your participation. 8 TPs have been ratified. It may be higher than that now on the 1.4, but about eight TPs have been ratified. And there's the website you can have to access them. Okay, NVMe-MI, just real quickly on the management piece. Management tools, have been around for a long time. It's critical that these management tools can talk to all devices and it's interoperable. So the management group, as part of the new feature set, is encompassing SCSI enclosure services. I think we all know that's been around a long time. That command set's been utilized historically across the SCSI environment. And now that'll be available to those applications and tool sets to access and get information on NVMe devices. We're also adding a in-band mechanism for those communications in NVMe, as well as the native PCI enclosure management that was just NPM has been approved, as well as part of the PCIe SIG just recently in August of 2017, a while back. So let's talk about the management features. Primarily, I would say most of the management today in all-flash arrays, as well as server systems, there's a baseboard management controller that's separate from the host controller that provides access to the devices and gets information, log data, thermal information on all the devices within a cabinet or enclosure, and provides that into the host. That's an I2C bus. Many are familiar with that, but it's called out-of-band management. It's not the primary communication path to the SSD where all the I/O traffic is. It's a separate I2C bus that comes in and connects these devices together to get information. For some of that information, what we're adding is an in-band mechanism across PCIe that allows the same information to flow across PCIe versus that out-of-band connection. So there's some start of day information, some boot information, VPD, vital product data, that when a drive presents itself, it gets shown up to the host as what that is. It's nice to have that directly connected to the host, such that they don't have to access the baseboard management controller or wait for that controller to be up. They can just access some of that information directly. And theoretically, you could even get rid of a baseboard management controller, but most people like to have those on board in case there's something wrong with the host controller. Allows the baseboard management controller to get the information still and present that up to the applications. NVMe over Fabric. I'll let Jay carry forward here.
Yes. Okay, so there's a couple things that we're going to be talking about today with regards to NVMe over Fabrics, and I need to be pinned here behind the podium, which is really difficult for me because I like to move. We're going to be talking a bit about probably the most worst kept secret of NVMe, which is the TCP portion of the NVMe over Fabrics. I'll be going a little bit further into detail about what the multipathing is and what it's not. And then I'll be talking a little bit about the enhanced discovery aspect of how these things work. And of course, we've got Peter and Amber here who are going to offer to keep me reined in from going a little bit over enthusiastically about some of this stuff. But the big news that everybody wants to know more about is the NVMe over TCP. So really quickly, let me get a quick idea of what kind of audience we're talking about. How many people here are primarily storage device oriented, for lack of a better word? Okay, that's a lot of you. How many people are network oriented? Almost nobody, one person. And how many people are pretty much host or virtualization oriented? Well, not again, 2 people, 3 people. Okay, cool. How many people just like raising your hands? About half, all right. There's always a few of you. All right. We have a series of fabrics that we can choose from in order to handle NVMe transports for NVMe over Fabrics. Now, you're probably very familiar with the common ones. You have the fiber channel, InfiniBand, you got your Rocky, you got your iWhoop, you got your ISO, we got your RDMA right here. That's what we're going to be playing with, right? Now, one of the things that became kind of obvious was we didn't have typical TCP. Yeah, say that 4 times fast. Typical TCP. And so what the NVMe working group started working on was the ability to create a fabric binding that would go into a TCP metaphor. And there's a couple of reasons why we wanted to do that. But before we get to the specifics about that, why would you want to do that? Well, a lot of the reasons about TCP is that it's ubiquitous. It doesn't require a special RDMA-based NIC, and you will pretty much find TCP networks everywhere in every data center. So that makes a huge difference when it comes to being able to handle storage traffic. Okay, so I'm going to go a little bit into the networking side of this just so that you can get an understanding of how this actually fits together. Effectively, what makes the NVMe over Fabrics Fabrics? What makes it actually a standardized thing or part of the specification is something called a binding. And a binding is what happens where you actually create the connection, the link between the NVMe layer and the corresponding transport layer. And those bindings are what make the actual transport friendly to the NVMe over Fabrics specification. You can't simply just throw a command inside of a packet and expect it to work over time. Right? There's a lot of things that you need to be able to do to make sure that errors are taken care of, that the authentication is taken care of, that the relationship between the host and the target is taken care of. That's all part of what we call the bindings. So you could theoretically throw an NVMe command inside of a TCP packet and let it go, but then if something went wrong, you really wouldn't know what to do with it. So what we do is we are creating a binding for NVMe inside of a TCP packet that allows us to create these commands and pin them to a specific TCP socket. Now what that means is that every queue pair that we have in NVMe is then associated with a TCP connection. Maybe I should stop back just really quickly. How many people are not familiar with the way that NVMe works? And I say the word queue pair, it's kind of... No? Everybody understands how NVMe queue pairs work? Sweet. All right. Well, you don't want to... We're winning. We don't have to worry about going back to basics. Okay. So instead of using a lower layer like a layer 2 approach for Rocky or a layer 4 approach that requires RDMA bindings, we can now do it with the TCP layer 4 basis where we're creating the TCP connections between a host and a target that then handle all of the queue pair relationships that are going on. Okay, so how does it work? One of the things that we wanted to be able to do was we wanted to use standardized NICs without having to have any kind of special hardware. Now you can do things like TCP offloading or those kinds of things, but let's keep it basic just for the sake of argument here, because that falls outside of the scope of the bindings anyway. So what we wanted to do is we wanted to create the ability to do NVMe connections between hosts and targets just using a standardized TCP approach. Now, that means that you don't have to have a specialized hardware driver to be able to run this, which is what you would normally do in a fiber channel or a InfiniBand or even an RDMA environment. So a software-only NVMe host driver can use the TCP stack to be able to transfer over the NVMe commands. Now, one of the reasons why you might want to do this is that right now, when we do any kind of TCP-related environment, you effectively have to do a translation. In other words, if you're running an iSCSI kind of an environment into a TCP backend, an NVMe backend that happens to be PCIe, you have to do a translation. And so what this allows you to do is maintain the multi-queue format from the host all the way through the target, even though we're running over a TCP connection. Now, this is much more efficient than having to do these kinds of translations. However, you still will have to deal with the fact that when we're doing the commands directly into a JBOF or an array or something like that, you're still going up and down the TCP stack. So what winds up happening is that you have the You have the normal latency that might be coming in a TCP, which means your TCP network has to be well designed, right? And now for those of you who are not networking people, there are ways of doing this that fall outside the scope of this presentation. But as we were talking about NVMe, Janine pointed this out at the very beginning, NVMe was designed from the ground up to be a performance protocol, right? So intuitively, you might be thinking, well, why would I want to do this from a TCP perspective if I'm going to be adding on microseconds of latency? All right, admit it. How many people would think about the question, why would you do this? Right? Okay. Just one guy in the back who likes to be that guy. The answer is that there are use cases that we would probably want to use for NVMe-based connections and connectivity. Effectively, what we want to try to do is we want to have the ability to have really large scalable systems. If you look at the way that TCP is currently implemented in say, a hyperscaler type of environment, you may still want to have block-based access into the actual arrays or actual JBOFs that don't necessarily have to have inside the host hardware to do this. For certain applications, you don't necessarily need to have the performance, but you should have the ability to have massive scale. So when you look at the kind of use cases, we're talking about pretty much of an iSCSI kind of alternative or a hyperscaler type of approach to being able to access and address TCP-related NVMe devices, if latency doesn't happen to be one of the things that is on your radar. That also helps keep some ubiquity. You can run TCP at the same time as other forms of NVMe devices. We're using the same kinds of Q-pair metaphors, which means that you could, for instance, run the DCB priorities and have like an RDMA-based Rocky v2, or you can run iWarp or some other type of RDMA-based approach for the performance aspect of things, while simultaneously having applications run at TCP approaches for non-latency sensitive applications. And so this gives you a little bit of flexibility because the Ethernet approach is actually quite flexible. You can do deterministic or non-deterministic storage at the same time. The other advantages that we have is the ability to have its own separate out-of-band control plane, which is something that David was talking about earlier. The ability to separate out the admin traffic as well as the management traffic on its own separate management plane means that you don't necessarily have to co-opt high bandwidth data lines for the administration aspect of things. That means that you can, if you've got a management network or several management networks that don't require an awful lot of updates, because let's face it, the admin queue stuff in the management queue doesn't really require as much bandwidth as the data does. So you have a lot of flexibility in environments like these that happen to be much more, I hate to use the phrase, but it's the best I can come up with, software defined, that you can actually be able to separate out your data traffic from your admin traffic and keep them completely separate inside of your data center. So that's another advantage that you might be able to apply for NVMe TCP. Now, where is this going to be? Well, basically, we're pretty much done. We're in the final stages of the approval rates for TCP. I think we're still in 30-day review. Is that right? We haven't started 30-day review? We're close, though, right? We're close. Okay. I wasn't on the call the last two times. I didn't know exactly when it was going to be done. But we're anticipating that this is going to be completed by the end of this year. We don't really expect it to find too much more heavy lifting work. The key thing about NVMe TCP, though, is it can't really be applied in isolation. Like a lot of the different things that we've been talking about, TCP is best when used with other aspects of things that we're working on. One of the things that we've been talking about, and this is part of the base specification that David was talking about, is the multipathing aspect. So when we start talking about multipathing, and from a networking perspective, multipathing is a little bit different than what we're here. But we don't have very many fiber channel or networking people here, if I remember the hands correctly. So I don't have to undo any damage there. But when we start talking about the multipathing from this perspective, realistically what we're talking about is the ability for a host and a target to communicate the nature of the path correctly. We've had sharing capabilities from our namespaces from the very beginning. We could share namespaces from a host to a target, and we would have the ability to measure that from a synchronous standpoint, meaning that if the paths were synchronous, they're exactly the same, the latency is exactly the same, we were able to handle this pretty well. But what happens when you start to go into different types of paths or distances? Sometimes you may want to make sure that the host knows that the target is asynchronous, not off, but asynchronous, right? So what asynchronous an asynchronous namespace access, which is a heavy-duty word to say this early in the morning, what that really means is when we have multiple paths from a host to a target, we want to make sure that the target can tell the host that there is something that is different between the two of them. And that communication that goes back and forth between the host and the target is what ANA actually does. So far, so good? Okay. I'm going to look at Amber because I don't want to screw things up. So what happens here is that when you have these kinds of environments with synchronous access, the host and the target are basically obviously in sync. There's not really much for the two to know about unless there's actually some kind of problem, which is an error condition. In a normal asynchronous mode, however, you still need to be able to have that communication between the host and the target. And so what we've been doing is creating modified approaches to being able to have that communication go back from the target to the host. And this allows us to have additional capabilities inside the NVMe specification. Now, for instance, if you were to look at an example of a fully redundant array, generally speaking, this is what we would find inside of a Fabrics. Right? So realistically, this was put inside the base specification, but you're going to see this a lot more often if you've got multipathing situations in a fabric. And that's true for Fiber Channel, it's true for InfiniBand, it's true for TCP, especially. All of these things kind of work together and being able to have that communication go back and forth between the host and the target. And as you can see, anything that can happen, especially if you're looking at a multipath approach in a highly congested network like TCP, that ability to communicate back to the host is going to make a big difference in maintaining performance over time. And so that's effectively what the ANA is supposed to do for both the PCIe version as well as for the Fabrics. Okay. When you combine this with a new thing called discovery, we've had discovery for a little while, but effectively what we want to do is we want to make this a little bit better, because what happens is we have a discovery controller that allows us to be able to pull the different types of characteristics inside of the devices that are on an NVMe system. And what happens is that the discovery controller has a list of the available devices and their characteristics, and you can pull those controllers to find out what's actually happening. However, it seems it's a pretty static relationship in a pretty static environment. And so what we wanted to be able to do is we wanted to try to remove some of the manual labor involved in getting the discovery controller to be able to provide communication to the different end devices. And so one of the things that we're looking at doing is improving a more dynamic association for discovery where you can have a more ongoing basis. Now that means that once we start to write things like the asynchronous logs into the discovery logs and so on, that means that those then become much more flexible and much more dynamic over time. So what we're doing is we're taking these different types of approaches, like, do one thing and do it well, and then we're stacking them and making them all work together. And so by being able to do this, we can fix some of the limitations of the way that these things currently work, which, like, for example, the discovery service can't tell if if something in a host is going to change, but when we start to work through this approach, we can then have a little bit more of a dynamic way of figuring things out. So ultimately what we're trying to do is we're trying to figure out better ways of connecting the storage consumers, which are the hosts, to the storage suppliers, which are the targets. And what that allows us to do is create a much more dynamic allocation for being able to grow and expand and move according to the needs of the data center. And so we don't necessarily want to replace some of the stuff that's going on in certain fabrics. For instance, we don't necessarily have to change some of the ways that Fiber Channel works, for instance, because we're keeping this above the Fiber Channel layer. And this is all going to be within the ability for NVMe devices to communicate with each other, and the transport is still agnostic underneath it. And it's true for TCP, it's true for RDMA, and so on. But what it does allow us to do is to create an environment where the fabric will know if something changes and can therefore react accordingly. Once the hosts have the ability to know what's going on, we can build intelligence into the host to figure out how they're going to approach certain types of transport requirements, and that gives us a greater degree of flexibility for a living, breathing data center. All right, so one of the things that we want to be able to do is find new paths when old paths are getting congested and so on. And so there's things that you can actually do to pull some of these approaches to make things a little bit less manual. Okay, so we have current limitations. Was it where are we now? Yeah, okay, good. We have current limitations on how the specification is. So right now, for example, the current NVMe over Fabric specification and Linux implementation limits our ability to discover these resources. And that resource enumeration is one of the things that we're looking to try to figure out and be able to communicate back and forth across an NVMe system. And so what we need to do is we need to be able to make a much more robust element for the communication aspect, which means that the logs that we write to have to be better accessible from a wider variety of devices. That could be hardware or it could be software. We need to be able to manage the Linux kernel driver stack as that it evolves, and we need to be able to make a much more dynamic approach to finding out the discovery route. And all of these different things are part and parcel of what we're actually looking at developing inside of the NVMe over Fabric specification. So one of the things that we don't do right now is we're just still talking about discovery. We're not talking about management of that discovery or the configuration at this point in time. That could be something that happens later on. But right now we're keeping things very simple and thin so that you're not trying to swallow the ocean at the same time. And ultimately, I think one of the things that's actually kind of important to note is that we've got over 50 active projects inside of NVMe. We were only able to talk about a couple of things here today. There's a lot of things that are happening which synthesize very nicely with a lot of these other projects that we've been working on. Remember that the base specification isn't just for PCIe. A lot of the stuff that's going on in the base specification is applicable across the board. Some of the stuff is available for just for PCIe, especially like the memory buffers and the persistent memory region is not necessarily a transport thing. But stuff like authentication, authorization, and management does cross a lot of the bridges that we're looking for. These are only the tip of the iceberg of the things that are working on inside of the NVMe working group, and we are constantly looking for additional contributors and people to help work with this. So if you're interested in participating in the NVM Express group, we would love to have you contribute into the technical working groups or even marketing for that matter.
Absolutely.
All right, that's all I got right here.
Okay.
So I think that brings us up to, well,
should have questions.
we should have questions. That was supposed to be the summary page. I'm sorry.
Hey, Janine.
Thank you, Jay.
Janine, why don't you say something about the marketing group and how it has separate meetings? And stuff?
Yeah. So just to kind of add on to Jay's comments. So we've got the base spec, we've got the NVMe MI spec, we've got the NVMe over Fabrics piece, the working groups. Then we also have the marketing group, and I co-share that with John Michael Hands from Intel. And essentially our key focus really from a marketing perspective is just to try to communicate out the spec, the standards, the information. We usually do all kinds of different activities throughout the year. We also are on Bright Talk pretty heavily. I think we do 4 or 5 Bright Talk discussions a year. And they're free. You can go out and check them out. We've done quite a few over the last couple of years, and they're very informative. So we try to kind of do that pretty frequently throughout the year. Just really, it's more of an education, an outbound education perspective. We just really try to get our messaging out, and there's lots of tools and resources available. So with that, I'm going to invite our fearless leader, Amber Huffman from Intel. She is the president of NVM Express, and I wanted to invite her as part of our Q&A session. David, do you have to run, or are you okay?
I think I'm okay.
Okay.
Don't get rid of David.
David's trying to get out of the Q&A. Something about a customer, I don't know. Anyway, so we'll go ahead and before we get started with the Q&A session, we actually have about 10-15 minutes for Q&A, so this is great. I did want to mention again, please follow us on Twitter, LinkedIn. Make sure you're checking out our website. We're constantly adding content and information out there. And also, please stick around for the next session, which will start directly after this one. I think there's a small break, and then we'll go ahead and get started. Some really great stuff. John Michael Hands is presenting. Chris Peterson from Facebook is going to talk about how they're using NVMe, all the benefits in their application. And then Chandra Chadha from Toshiba is also going to be talking about enterprise data centers. So please stick around for that. So with that, we'll go ahead and open it up for QA. You got some great experts right here. So nobody start at once.
Nobody wants to be that brave.
Everybody knows everything.
I should have got free swag.
Well,
First person.
If Peter was up here, people would be asking questions.
Anybody? Okay, so two things. Either A, you're all asleep, which hopefully you're not, or B, we told you everything you needed to know. So it was a great informative session, and you're going to go buy a happy cup. Yay! Come on!
So looking at the standards, when can we expect if ratification is the end of this year, when can we expect to see things rolling out into vendor products? What's the typical sort of timeline we can expect?
Well, it often depends on. Oh, David's getting a call.
No, it's not my bad.
Nope. Oh, Janine's getting a call.
Janine's getting
So
Naughty.
typically one thing that occurs is it depends on the type of feature we're talking about, right? So, for example, the NVMe over Fabrics TCP, I think that a lot of it is leveraging existing NICs and whatnot. And many people are, I believe you're going to see several demos of this at the show today. And so I think that you may even see coincident or very shortly thereafter by end of year to have products that are consistent with the TCP. There's many of the features that are very similar to that. Anybody else want to take a stab at...
Well, I think that the important thing to note is that none of these things exist in isolation. So there are a lot of stars that have to align to get a working system. The TCP stuff, for example, may get the transport stuff sorted out, and you maybe have the connections between the host and the target, but that doesn't necessarily mean that you've got things like high availability sorted out, for instance, or virtualization on the drives, or if you're just using a JBOF, that the software-defined storage that would be connected into them have the APIs done correctly. So this is really just one piece of a larger puzzle. And so I think that the standard rules apply, which is that the vendors are going to be coming out with the alpha and beta and releases for different solutions. I honestly think that it's understandable that we're going to see a lot of startups that are going to have, because they can move a lot faster than some of the more traditional approaches, and they're going to offer up some great proof of concepts and testing opportunities, and probably the typical life cycle of testing and qualifications are going to apply. I don't think there's any shortcuts here.
And just to add in briefly, features, we ratify them as we go. So, for example, we've already ratified persistent memory region, even though NVMe 1.4 won't come out for another year. So you may see products in the marketplace that are persistent memory region even ahead of us shipping the official 1.4 spec. So that's where we're always trying to make sure people can move forward with innovation. If it's a firmware-only feature, it can happen very rapidly. And if it's something that requires hardware impact, then your typical hardware ASIC timelines apply.
Yeah, you don't have to wait for a generational spec to come out. You don't have to wait for 1.3 or 1.4. Once those items are ratified, like Amber said, they can be, you have confidence in those things are defined.
This gentleman had a question?
TCP and UNH. I see you rocking on UNH. Do you folks have any insight on the IOL interoperability of the PCB?
Well, so you're asking two different questions here. One has to do with the compliance part of it that the University of New Hampshire has with the interoperability lab, and the other has to do with the TCP spec, right? Right. So we do run about twice a year, roughly, plug fests that go into UNH and run in the interoperability lab. We generally try to wait until the actual spec is far enough along to warrant a plug fest for it. To that end, the latest plug fest just happened, and so we didn't make the time frame for a UNH plug fest. But we haven't had the conversation yet. But it's entirely feasible that we may be doing that in the next plug fest. We haven't discussed it yet, though.
So when they'll appear the session tomorrow afternoon, the University of New Hampshire will be here, and they'll talk about their plans for TCP.
do you expect the performance differences to be between connections over TCP versus RDMA?
Well, this is where I deliberately didn't go into that particular part of it because it has to do with the way that network architectures are. So, for instance, once you get outside of the host, all bets are off when it comes to performance. And the reason is because you can have a really well-architected TCP network, or you can have a really poorly architected layer 2 network. And so the issue is that, are there things in TCP that you can use to help augment performance? The answer is yes. There's something called the data center TCP. There's something called deep packet prioritization. There's some QoS and quality of service stuff that you can do inside of a network that affects both L2 and L3 and L4 connectivity. But it will make a huge difference as to how much bandwidth you allocate at a given time, what your links are. So realistically, the problem is that depending upon how many hops you have going over a number of switches, it's like the weather. You can predict what's going to happen in the next 5 minutes, but in the next 5 days, things are a little bit strange. And once you go over that threshold, it gets a little bit more difficult. But what I was going to say was that the layer 2 stuff, the Rocky stuff, for instance, is usually pretty much a deterministic storage system. And so I think what's going to happen is the variability is going to be better for a Rocky-based system than from a TCP-based system, just based on the way that L2 networks and L4 networks are usually designed and implemented.
And if we just step back to the 1,000-foot level of NVMe over Fabrics, if we compare it to, say, iSCSI, one of the biggest issues, regardless of what your flavor of transport underneath is getting end-to-end NVMe is a huge win. And what people consistently see is if you are end-to-end NVMe, you have multiple queues, you have all of these capabilities of NVMe that you can use all the way to wherever the target is, versus translating through SCSI, getting into one queue, all of those things. And so the biggest win comes from getting on NVMe to begin with. And then, you have to, again, go to where Jay's going of the particular network architecture and how you want to optimize. That's why we have fiber channel, we have RDMA, and then now we're adding TCP. Is different people need different things for their own architectures, but getting on NVMe is certainly the uniform point of advocacy of benefit that you get at a big picture.
There's also work going on peer-to-peer within those devices in the network. So there's some new advancements going on with respect to that as well, which will be very interesting.
Yeah, it's one of those things that the more we start to dig into this, the more options you find that you have. And the more options that you find that you have, the more work you have to do, right?
More innovation. Come on, Jay.
More innovation.
It's all
part of innovation.
positive.
But ultimately, what it boils down to is that there is no such thing as a no-brainer when it comes to networks, right? So when you start to figure out whether or not management is your priority, your scale is your priority, or your performance is your priority, that's when you start to take a look at the way that the different networks stack up against each other. And there's a bunch of different hands going up. Great.
If I make a plug for TCP, am I allowed to?
You can plug away. Go for it.
Because you're talking plug first, no transmitted. But relatively wrong.
Well, I think you're just reiterating, perhaps maybe get to NVMe, and then you're really going to have to figure out what you need for your network, right?
Right.
But the performance is not like half of the other guys.
No,
It is not even that far, not more than a little bit far.
And that's fair. So in case you couldn't hear, his point was that in rudimentary testing there was a minimal difference in latencies between and IOPS in terms of the difference between the different transfer protocols, and I think that in a perfect world you're not going to see all that much difference because the benefits of NVMe are pretty universal.
Well, I'd encourage people to go to the different booths because you're going to see a lot of implementations.
Oh, yeah.
That are pretty interesting across
argument.
the different vectors. Go
Completely
ahead.
agree.
There's a patient gentleman in the back there.
Thanks. Going back to the NVMe spec, do you think about PCIe spec of like 1.4?
It is literally, as you guys know, I mean, PCI SIG is already working on PCIe Gen 5. It literally doesn't matter to us underneath. So if there's a feature underneath that would matter, at times we care a little bit about advanced error reporting and whatnot, but generally what's underneath it does not matter. So it's with the backwards compatibility of PCI SIG. If there's anything that we do need to be cognizant of, so for example, the persistent memory region, that is one where it is kind of a PCIe feature, but Peter's based it very heavily on widely known, stable parts of PCIe specs, so the generational speed does not matter. So we're ready to go for Gen 4 and then, hopefully a quick turn to Gen 5.
Any other questions? I think we got time for one more. Oh, we got two. I'll take you first because you put your hand up, and if we have time, we'll get to yours, okay? Go ahead.
About the directional? Oh, bidirectional commands. So I think there's an active debate of, do we ever want bidirectional commands? And so people will go back and forth, and there's some people that feel like we should never have bidirectional commands, and some people that feel like we should. My money is on we probably continue to not have bidirectional commands, but Peter, do you have a...
I'm with you.
So it will be an active point of excitement if we end up with bidirectional, because it opens up a new vector of complexity that we have not been wanting to go down, but we've left it as a reserved option.
You get more cooks in the kitchen.
I think we got... Go ahead.
What are the applications for the new persistent memory region?
So a key thing about the persistent memory region, and Peter may add in since he was the lead author, is you may have implementations where you essentially put some fast non-volatile memory, whether it was a phase change memory or 3D crosspoint or whatnot, and you want a fast path to get to that faster memory than the base NAND. And so with that persistent memory region, it's non-volatile. It might even just be memory backed by a capacitor or battery or whatnot. And so it allows you to go and squirrel away data or other capabilities right there and have it still be there when you come back. It's equivalent to the controller memory buffer for all intents and purposes, but it's just non-volatile.
I understood that, but what are the usage cases?
All the metadata and
Yeah, there's some host metadata that they like to have persistent down into a device and stage, so that if a device goes away and comes back up, they have some additional state information about those end devices.
I think like write-ahead logs for key value stores, that's not a really good application for it.
And another of our future speakers, Jim Harris.
All right. Well, I think that concludes the time that we have today. I encourage you to stick around for the next track. We'll be starting here in the next, 10 minutes or so. Thank you so much for attending this morning. I know it's always hard getting started in the morning, but also too for help working through our AV snafus that we had to kind of deal with this morning. I appreciate your patience, and hopefully this first track was engaging. It definitely, I think, was a good way to...
And a big thank you to Janine and John Michael and Brandon for getting all of this put together. So.
Yep.
Awesome. Okay, well, we'll be back here in a few minutes. I encourage you to stick around. Thanks again.
Thank you.